I work at the Space Sciences Laboratory at the University of California, Berkeley. And I'm also an instructor at Berkeley City College. I teach physics and astronomy there. And so today I'll talk a little bit about Solar Max, about our sun, its activity, and then what that affects, impacts on Earth. So let's see here. Ahead. Uh-oh, there we go. So there's a nice picture of the sun, not usually how we see it when we look at it, but I'll talk a little bit about that in a bit. But sort of very briefly, just want to talk a few minutes about the sun itself, just some general properties, and then what we mean when we say solar activity, how the sun is active, and then how that activity changes over time in what we call the solar cycle, where we have solar minimum conditions and solar maximum conditions. We'll focus on the maximum part. And then what effects that can have on Earth and on our technology, a topic that we sometimes call space weather. So I'll say a little bit about that too at the end. So to begin with, the sun is a star. So it's the closest star to Earth. It's the one that we can study the most because it's the closest to us. And turns out the sun is really big, at least compared to us. It's over 100 times larger than the Earth, about 110 times actually. But it has about 300,000 times more mass. So it's the largest thing in our solar system. It's about 99.9% of the mass of our solar system is all in the sun. And then you have these tiny planets over here. And so you can see, there's the little balls next to the big ball. So the big ball is the sun. And the little balls, you might be able to see Jupiter, Saturn, and then one of these small little tiny ones is Earth over here. So for size comparison. So it turns out the sun is hot. So the surface or the part of the sun we see is about 5,500 degrees Celsius or about 10,000 degrees Fahrenheit, depends which unit you like better. And the center is about 15 million degrees. Doesn't matter if it's Celsius, Fahrenheit. It's really hot either case. And so this is important. The sun is so hot that molecules can't stick together, or atoms can't stick together for molecules. And actually, the atoms themselves have trouble sticking together. And so everything is ionized. So the electrons can't stick to the atoms, and so you have a big hot ionized gas floating around everywhere throughout the entire sun. And that will be important later. The sun is made mostly of hydrogen, just like most things in the astronomical objects in the universe. About a quarter of the sun is helium by mass, and 2% everything else. So there's oxygen, there's carbon, there's lead, there's gold, all that stuff's in the sun. It's just a very small fraction of the sun's mass. And let's see, the sun is pretty bright. Let's see, if you want to put it in terms of light bulbs, it's about 400 trillion 100 watt light bulbs, which is a meaningless number. It's just huge. But at Earth, we get about 1,370 watts per square meter at the Earth. We call it the solar constant. That's basically how much energy we get from the sun almost all the time. It varies very little over the course of a year or a solar cycle. Okay, talk a little about what's inside the sun and outside the sun. So the center of the sun has layers. The center is the core. That's where the sun produces its energy by fusing hydrogen into helium. So that's how all stars get their power, including the sun. It's the same kind of thing that people in Livermore try to do at the Livermore National Lab. They're trying to do fusion in the lab. It's really hard. It takes a lot of energy on Earth. It's really easy for a star because in the center of a star, things are really, really hot and really, really packed close together. And so it's a lot easier to fuse that hydrogen into helium, and that gives off energy. And that energy moves through the sun. And so it starts out moving through what we call the radiative zone. So the energy that's produced in the core moves by radiation. So that is basically by light or by photons traveling through that zone, carries energy away from the core. And then a little bit further out, we have the convective zone. And there, energy is transported by convection. So basically, you can think of the sun, those outer layer of the sun there as sort of like boiling. So you have this ionized gas that's really hot, moves up, cools off, moves back down. You have these big convection cells or stuff traveling from this interior of the sun to the surface and giving off and carrying energy that way. Then we have the photosphere. That's what we call the surface of the sun, but it's not a solid surface. The whole thing's ionized gas. But we call it the surface because it's the part we see. When we look at the sun, the part that our eyes see is what we call the photosphere. But like I should warn you, don't stare at the sun. It's not good for your eyes. Unless you have the correct filters, then it's fine. But that's the part when we look at the sun, the part we see we call the photosphere, which just means that's where the light comes from. It's a light sphere. So that's just the part that we see. There are layers above that, which we call the atmosphere of the sun. But again, the whole thing is gas, so it's kind of silly to say atmosphere. So above the photosphere is the chromosphere. So chromo means color. So that's when we look at it, it usually appears red. And we can usually only see that during eclipses. And that red color comes from hydrogen atoms. So let me show a quick picture. This is a picture of the photosphere. So that's usually what we see if we have our nice filters. We can look at the sun. You see some sunspots there. I'll talk about that in a minute. Here's a picture of a solar eclipse, and we can see that little red ring around there. That's the chromosphere. So there we have hydrogen atoms. They're really good at emitting red light, and so we're seeing in that little red ring. And then further away from that, we have the corona, which we call the outermost layer. And so that's sort of the white wispy stuff that's further away than the corona. And that, interestingly, is over 1,000,000 degrees. So usually things cool down. Which start at the center, it's the hottest. You move away from the center, things cool down. That's the case for the interior of the sun. It goes from 15 million degrees to 5,000 or 6,000 degrees. But then it heats back up again once you reach the corona. And becomes up to 1,000,000 degrees again. But it's very, very, very diffuse. So there's not a lot of stuff in the corona. It's just really hot. And again, we'll talk a little bit about why we think it's so hot. And that corona expands out in space and basically becomes the solar wind, which is just basically the outermost part of the sun's atmosphere. You just have basically streaming throughout the entire solar system is the solar wind, and it's just the outer layers of the sun flowing away into interplanetary space. Okay, so we talk about activity on the sun. Now, we look at the sun, doesn't seem like much is going on. But if you look at it for, years, you'll notice some changes. And so the most well-known indicator of solar activity are sunspots. And so these are dark spots in the photosphere. As we see here, a nice picture of the sun. There's some actresses from a couple days ago, I think, when I was putting this together. That's what the sun looked like a few days ago. Probably looks about the same now. But you see some sunspots around the sun. They appear darker because they're cooler, about 1,000 degrees cooler than the surrounding photosphere. But that's still really hot. It's still, over 4,000 degrees Celsius. It's just compared to the 5,500 degrees Celsius, it looks a lot dimmer. So these sunspots usually last from weeks to months. Sometimes they'll grow in size and then shrink in size again. They come and go, but it takes them a few weeks to a few months to come and go. And the sunspots come from or they're caused by magnetic fields in the sun. So I have another picture here that is a zoom in, an artist's rendition of what this looks like. And so we have strong magnetic fields, underneath the photosphere in the interior of the sun, but sometimes they can poke through the photosphere, as this picture illustrates. And you'll have a little loop of strong magnetic field poking through the photosphere, and that basically stops and inhibits the convection going on underneath there. And so it turns out because the sun is made of an ionized gas, a magnetic field can tell that ionized gas where to go, or in this case, where to not go. And so the magnetic field here is containing more energy than the ionized gas. And so it prevents the ionized gas from moving and convecting and having hot material rise from above. And so the ionized gas is stuck there and it cools off and gets cooler and darker. I will also note that the opposite can also happen. If the ionized gas contains more energy, it can drag the magnetic field until the magnetic field where to go. So it really depends, which has more energy, which one tells who where to go. If the magnetic field has more energy, it can confine the ionized gas. The ionized gas has more energy. It can drag along the magnetic field with it. And so as this picture illustrates, some sunspots also come in pairs. So you have, as it says here, a north pole and a south pole, like a magnet, because it is the magnetic field. And so whenever you have a magnetic field, you have a north pole magnetic field and a south pole magnetic field. And so sunspots come in these two pairs illustrated there. And here is another picture of the sun. This is basically a picture of the magnetic field of the sun. And again, this is from a couple days ago. So it corresponds to that this same picture with the sunspots. There's a picture of magnetic field. And so you can see the red, orange areas, and then the green, blue areas. Those are opposite polarities. So I don't remember which one's north, which one's south, but they're opposite polarities. One color is north, one color is south. And if I flip back and forth, you can see where you have strong magnetic field. Whoops, this way. You also have the strong sunspots. And so you can see one right here. There's a nice sunspot there. And they have a very strong, very dark blue magnetic field. And you say, where's the opposite polarity? Well, it's more spread out. You can see this, there's some yellow, orange stuff here. It's not as concentrated, but it's still there. So you have strong polarity one way coming through the photosphere and more dispersed going back into the photosphere. Same over here. We can look at this spot, or these spots, I should say. There's several spots there, and you can see clumps of very, very strong red magnetic field and very strong blue magnetic field, and there's more red, and so you can see the opposite polarity there of the sunspots connected to the magnetic field coming in and out. Okay, so not only sunspots, but associated with these strong magnetic fields and with sunspots, because the sunspots associated with strong magnetic fields, are things we call prominences. And so these are, as well as solar flares and coronal mass ejections. So we'll talk about each one of them in turn. But prominences, there's a picture here, is a big loop. So it looks like a big loop of glowing hot ionized gas. And these can last days, 2 weeks. And at the base of these loops are sunspots. Now, in this picture, the sun looks different than it did in this picture. And that's because we're looking at ultraviolet light rather than visible light. So our eyes can't see the sun looking like this. We have instruments that look in ultraviolet and can see things that our eyes can't see. And so in visible light, our eyes wouldn't see this thing. It would look, well, at best very faint, but usually invisible. But when you look at other wavelengths, the shorter wavelengths in ultraviolet, these things become more visible. And we can see that the sunspots, which would be dark invisible light, are actually kind of bright here in ultraviolet light. And it's because of this very hot ionized gas that's held there above the photosphere by the sun's magnetic field. And so we see that hot ionized gas emitting light in the ultraviolet. Okay, so here's just a picture showing, okay, here's the ultraviolet light, where you can see these big loops and that hot ionized gas stuck on those big magnetic field loops. And they're very bright down here near the photosphere, but in visible light, what our eyes would see, those are sunspots, those are dark areas on the photosphere, and we don't see those big bright loops here in visible light, but we can see them in ultraviolet light. Okay, so also associated with prominences, sometimes we see solar flares. And solar flares are explosions in the sun that basically last from seconds to hours. And again, these are not seen in visible light, but they're often seen in ultraviolet light and even X-rays. And so here's a sequence of images showing visible light. We see the dark spot here, that's the sunspot. And ultraviolet light, we see these big loops. It's very bright down there. And in X-rays, we see actually a really bright spot. And it's actually, so bright that it sort of overwhelms the detector. And you see these weird spikes coming to the side. That's not real. That just means it's really, really bright. It's overwhelming the the camera that's looking at it. And I have another little animation here. Here we go. So this again looking in ultraviolet light, and we can see, can see the big loops, and you see that it gets really bright all of a sudden right in the center of the image. So that increase in brightness is what we call the solar flare. You have a big spike in brightness in ultraviolet light and X-rays. And we can see that it's associated with those big loops of magnetic field that coming out of the photosphere. And you can actually see there's another big bright region over here that also has these big loops coming out, and so we can see. Well, this one is a flare. This one may have flared earlier. It's not quite as bright in this image, and just over the limb of the sun. But there's two big bright spots there, but very active. Okay, and so it's just a still image, but you see that again that bright solar flare happening. Okay, so like prominences and sunspots, the solar flare is associated with regions of strong magnetic field. Okay, and so the idea here, at least the idea we have in our head, is that this big bright release of energy in a solar flare is a result of the magnetic field rearranging, and so that the technical term we use is we call it magnetic reconnection. Basically, just the magnetic field rearranging itself. And when that happens, the energy in the magnetic fields, the magnetic energy, is transferred to the ionized gas, and it heats it to tens of millions of degrees, and causes that ionized gas to emit ultraviolet light and X-rays. We think also this process helps heat the corona. Remember the corona that was 1,000,000 degrees on average? So whenever you have these events that heat, that ionized gas locally to tens of millions of degrees, and that can just, basically disperse and heat the entire corona. And so here's that little, what we call X point, where basically the magnetic energy is transformed into the ionized gas, transferred and heats and energizes all that ionized gas. And you can see that sort of pinches off right there, and then some of that material goes back down the photosphere and makes those really bright loops that we see. But you can see that some of this material goes away from the sun. So what about that? And so that is what we call a coronal mass ejection. And so that's the part, of this whole configuration that moves away from the sun. And so these are ejections of mass, primarily ionized gas, from the corona. So they go through the corona and away from the sun. That's why they're called coronal mass ejections. And so these are all often associated with solar flares. Not always. There's not a one-to-one correlation, but usually, almost always, when you have a solar flare, you'll have a coronal mass ejection. And so the coronal mass ejection can eject about 1 billion tons of ionized gas, several hundred to a few thousand kilometers per second away from the sun. This sounds like a lot. It is a lot, but the sun's really big, and so a few billion tons is no big deal to the sun. That's a small fraction of the sun, of the sun's entire mass. But for us, it's a whole lot. And so these coronal mass ejections can expand and travel throughout the solar system. And so I have a couple animations here. This is from an instrument that looks at the sun, and this particular one is what we call a coronagraph. So the sun's the center of the image, but we put a little disk in front of the sun, and so that white circle is where the sun would be. But the photosphere is really bright. And so we're going to block the light out from the photosphere so we can see the much dimmer corona. Usually we can only see that during a solar eclipse, but if we put this little disk there, then we can make a fake little eclipse so we can see the corona. And in this case, you can see a coronal mass ejection. This is over the course of about 4 hours or so. You can see it expand and enlarge and just move out into space. And we also have a zoomed out view. So here's another coronagraph, but now that circle in the middle is smaller. So we get a larger view of the space around the sun. And we can see, yeah, that coronal mass ejection just continues to expand and get bigger, and it goes throughout the solar system. Sometimes it runs into Earth, and we'll revisit that here in just a minute, and what that does for us. Okay, so turns out for centuries we've been watching the sun. Well, actually, for millennia we've been watching the sun, but we've been keeping uh, uh, basically good records, I guess, for centuries, continuous records for centuries. And we've known the number of sunspots changes with time. So here is going back to 1750, so not quite 300 years ago, 300 years of looking at sunspot numbers. And actually, there are records that go back, continuous records that go back another 150 years. And then we have spotty records that go back thousands of years. But continuously, we have good records back for 250, almost 300 years, and some records that go back even further. But these are the ones that we're pretty sure are continuous and more confident in. And so we've been watching the sun, and we can see the number of sunspots changes. So it's a sunspot number, and sometimes there's no sunspots in the sun, and sometimes there's several hundred. And so this cycle and the changing number of sunspots is called the solar cycle. And let's see, since we started keeping good records, we've gone through 24 solar cycles. We're in the 25th right now, and so here we're near. This is us right now. Actually, it's probably been a few more points since this picture was made, but we're basically in the middle of what we call cycle 25, near the maximum in the number of sunspots. Okay, so if the number of sunspots changes, then that means the number of prominences is changing, because prominences are associated with sunspots. The number of solar flares is changing, and also the number of coronal mass ejections is changing on that same cycle, so that same solar cycle. And typically, if we look back here, that cycle lasts on average about 11 years between peaks in that cycle. And so when there's a peak in the number of sunspots and the number of solar flares, the number of coronal mass ejections, we call that solar maximum. And when there's a minimum, we call that solar minimum. So at solar maximum, there can be over 100 sunspots on the sun at any time, sometimes even more, 200, 300. And you can have several solar flares and coronal mass ejections per day. During solar minimum, you can have very few, handful of sunspots, even no sunspots on the sun at a time, and you can go for a week without a solar flare or a coronal mass ejection. So a big difference in the sunspots and solar flare activity from solar minimum to solar maximum. Okay, and we know that all of these phenomena, sunspots, prominences, solar flares, coronal mass ejections, are related to the sun's magnetic field. And so that tells us the sun's magnetic field is changing every 11 years. And so here's just a map, well, basically pictures of the magnetic field of the sun, showing that during solar minimum, the sun's magnetic field is not very structured. It's all very, blah, not any big regions of any one color. And as time goes on, you have all these regions of strong magnetic field, again, that are associated with sunspots and flares and coronal mass ejections. And so this is what we call solar maximum of cycle 24. So about 5 years ago, well, almost 10 years ago now. And then basically the structure of the strong magnetic field decreases again over time, and you go back to solar minimum. So we're in solar maximum now, 2025, 2024, 2025. The previous solar maximum was around 2013. Again, it's not a particular time, but that solar maximum can span a year or so. So maybe 2012 to 2014. Had lots of sunspots, lots of structure in the magnetic field, right? Solar maximum. So why does magnetic field change? Why do we have the solar cycle? Okay, so to that we have to basically think about, why does the sun have a magnetic field at all? And then think about why that magnetic field changes. So whenever you have a moving charge, you can create a magnetic field. The sun is made of moving charges. It's all ionized gas. So all those charges are moving around, and the sun is rotating, and the sun's convecting. We have that convection zone. So things are moving around all the time. And so those combined motions give rise to what we call the solar dynamo that generates the sun magnetic field. And so the dynamo, my dynamo theory is just how you get moving basically charges to generate the magnetic field. The same thing happens, well, a similar thing happens in Earth's core. So the Earth's outer core is made of liquid iron. So that's a basically a conductor, a charge. And Earth rotates, and that outer core is hot and convecting, and so it generates Earth's magnetic field. We call that a planetary dynamo. Same idea, that you have all these charges moving. And so in the sun, we've got the solar dynamo. Okay, so you can generate a magnetic field just by having stuff move around. But then why does it change? So it changes because the sun isn't a solid body. It's just made of ionized gas. And so some parts of the sun rotate faster than other parts. So near the equator of the sun, it takes about 25 days for that ionized gas to rotate around the center of the sun once. If you go up near the poles, it takes a lot longer. It takes maybe 35 days for material near the poles to spin around the sun's rotation axis. And so we have a differential rotation. So some parts of the sun are moving faster than others. And so in this case, now in the big solid bit of the sun, there's more energy in the ionized gas than there is in the magnetic field. And so the ionized gas starts to drag the magnetic field. So the magnetic field starts out, more or less, nice and simple and uniform. But as the sun rotates, as the equator rotates faster than the poles, the equator sort of drags that magnetic field. And what happens, it takes an initially north-south magnetic field, and you pull on it sideways, you bend it, and it becomes more of an east-west magnetic field. And so the idea here is that you start with north-south field, and rotation drags it into an east-west field over the course of several years. And you can have parts of that east-west field, these east-west loops, can pop up through the photosphere. And when that happens, that magnetic field pops up. Well, where it pokes through the photosphere, that's where we see the sunspots, and that's where we see the prominences, and that's where solar flares can occur, and where coronal mass ejections can be launched from. And so that's basically that. As you twist up the magnetic field, it becomes unstable. Bits pop up, and that's it gets its maximum at solar maximum, where you have the most loops popping through the photosphere. But again, over time, you have the large-scale circulation patterns in the sun sort of drag those strong field regions toward the poles, again, over several years. And then you eventually, we think, get to the point where you have strong field over the poles, it's more north-south, and the whole process starts over again. So this is the general idea. There's a whole bunch of details we do not understand at all. And people are still trying to figure out, okay, how the details of all this works. But we think that's a general idea of twisting up the magnetic field, becomes unstable, and regions pop up above the photosphere, and then circulation brings those strong field regions back to the pole over time. Again, this whole cycle takes about 11 years to go through all these different, A, B, C, D, E, F, G, H, I. Okay, so that's why we think we have a solar cycle, and what's causing it. So the question that you may have is, well, what's the effects on Earth of this, changing sun magnetic field and the changing, activity on the sun, the changing number of sunspots and flares and coronal mass ejections. So for most of human history, there really was no practical effect that on the Earth. The only effect that people would have seen due to the solar cycle was basically the occurrence of aurora, at low low latitudes. Here's some pretty pictures of the aurora. Usually, we think of that occurring, in Scandinavia, in Alaska, maybe in northern Canada. That's people where usually people go to if they want to go see the aurora. But sometimes it comes, to lower latitude. And so here's a picture just from last year, from Tilden Regional Park in the East Bay, not far from where my office is. And you can see, aurora all the way down in Northern California, which is unusual. But we're near solar maximum, and so that occurs, at lower latitude more often. So it turns out whenever you have one of these coronal mass ejections hit the Earth, the region where you're likely to see the aurora, which is called the auroral zone, expands equatorward, and we call that a geomagnetic storm. So here's two model pictures, I guess, but on the left here is basically where you normally would expect to see the aurora. They're in green, so in Scandinavia, Greenland, Iceland, maybe northern Canada into Alaska. When you have a geomagnetic storm, so basically when a coronal mass ejection hits the Earth, that region expands toward the equator, and so you can see here it's much broader and goes to much lower latitude. And you imagine the Earth is rotating underneath this pattern. So sometimes, in this particular snapshot, it's daytime here, it's nighttime there, but Earth rotates, and sometimes we can when it's nighttime here, we can see some of that aurora down to lower latitude. Okay, and so why does how does that work? Well, basically, it has to do with how this coronal mass ejection interacts with Earth's magnetic field. Okay, so the aurora usually occur on Earth more or less, near the North and South Pole, and that's due to the configuration of Earth's magnetic field. So the top picture shows sort of the general case, undisturbed case. Here's Earth's magnetic field, and there's basically rings around the North and South Pole of where the aurora can be seen most commonly. This bottom little animation is a computer simulation of what happens when a coronal mass ejection hits the Earth. And you can see here, Earth's here at the center, but all these white lines are magnetic field lines. You can see Earth's magnetic field. And then that coronal mass ejection hits Earth's magnetic field, it gets compressed. And you can see how much it shrinks. And so that basically allows the region of the aurora to move to lower latitude. So you're changing the shape of Earth's magnetic field due to this big cloud of ionized gas from the sun hitting the Earth. And so that's why we can see aurora at lower latitudes. Okay, so again, before we had any electronics, before I had any fancy satellites, that was really the only effect that humans could notice in terms of the solar cycle. That every 10, 11 years, you could see aurora at lower latitudes than normal. And of course, people would write down all this stuff. And so we have records, going back centuries and millennia of when, oh, wow, we had aurora here. That's really unusual. But nowadays, there's a lot more effects that the sun and solar activity can have on the Earth. Because much of our technology can be affected, particularly by the solar flares and also by coronal mass ejections, which again are associated with the sun's changing magnetic field. And so we're going to stop from the top and work, out in space and work our way toward the surface at some of the effects this can have on humans and our technology. So the first is basically astronaut safety. So astronauts are there above the atmosphere on the space station and whatnot. And so they're not protected by the atmosphere. So the atmosphere actually protects us on the surface from a lot of the energetic photons, that's the ultraviolet and X-rays that come from solar flares, and the energetic particles, so that's the ionized gas that gets accelerated toward the Earth in the coronal mass ejections. And so the atmosphere basically absorbs a lot of that. way up high, so it doesn't reach the surface. But if you're above the atmosphere, you don't have that protective layer. And so these very energetic photons and very energetic particles, we call them ionizing radiation, because when they hit an atom or molecule, they have enough energy to break that molecule apart, or to ionize that atom and eject some electrons, and basically change the chemistry of how that works. As that can damage cells, and biological tissue, and so that's a bad thing. And so during large solar flares, the astronauts can be exposed to the equivalent of thousands of chest X-rays, in the span of an hour or so, which is again, that can damage basically the cells and their body, and so we don't want that. And so there's lots of shielding is required on the International Space Station, especially in the regions where they spend the most time. So in the sleeping quarters and the eating quarters, they have lots of shielding around there to try and decrease the effect, minimize the effects of being outside the atmosphere. And so there's been several instances where you have solar flares, and you have little alarm, and all the astronauts have to go huddle in the most protected part of the space station, again to try and decrease the harmful effects of these very energetic X-rays and very energetic particles. Okay, we also have lots of satellites up there, a whole bunch of satellites up there, and they can be affected by both the energetic photons from solar flares and the energetic particles that come from solar flares and coronal mass ejections. And so one way they can be affected is by what we call deep dielectric charging. So this is something that happens over time. We have this is mostly from energetic particles that basically hit our satellites and can basically build up and damage the circuits. Have enough charges that hit your satellite eventually can have a short circuit and basically zap your satellite. And so you can mitigate that with shielding around all your electronic components, but the more shielding you put on there, the heavier it is and the more it costs. And so there's a trade-off between how much shielding you want versus how much protection, versus how vulnerable you want your systems to be on your satellite. And so that's something we can people can study and say, okay, make a design lifetime. Okay, we think this electronics will last this long in this environment, so you put X amount of shielding on there to make it last that long. We can also have what we call single event upsets. So this is a one-off thing that happens. It doesn't take not over many years, but just all of a sudden. So again, you can have an energetic photon or particle that's basically just hits the electronics just right, and basically if the little computers on there are reading numbers or spitting out numbers, it can basically change what that number is. We call it bit flip. So change a 1 to a 0 if they're all your things are done in binary, and that can give phantom commands or make the spacecraft do something you don't want it to do, and that's you can basically lose the spacecraft that way if it turns itself off or turns itself in the wrong direction or does something. And so there are mitigation strategies for that. And so if there are a bunch of energetic photons or particles coming, you can basically turn off those sensitive electronics, not have the computer, basically talking back and forth at that time. So there'll be no bit flip, there'll be no phantom commands. And so you can go to safe mode, which is basically you turn all the electronics off, during these events. And sometimes if you don't do it, that can happen anyway. Again, due to single event upset, a spacecraft can go into safe mode. It'll turn itself off because it gets all these weird commands it wasn't expecting. And so that can be an issue for satellites as well. Let's see, if anyway you have solar panels on your roof, then you know that solar panels do degrade over time due to just basically the elements on our surface, but including ultraviolet light above the atmosphere. The energetic photons, ultraviolet light and X-rays, are much more harsh, and you have the energetic particles hitting it, so you have its own set of elements up there that degrade solar panels over time. And again, we know how that works. But when you have a solar flare, or when it's energetic coronal mass ejections, there's a whole bunch of energetic particles hitting your solar panels all at once. You can have a year's worth of degradation again in just the course of a few hours. And that really decreases the lifetime, or can decrease the lifetime of your satellite. And there's really not much you can do except try to design it to withstand that. And another important effect on satellites is atmospheric drag. So during solar max, when you have a lot of solar flares and these coronal mass ejections, basically the upper atmosphere is heated and expands. That increases the drag on low Earth orbiting satellites. And so in particular, I know that Starlink, there's a whole bunch of those satellites up there, but there were a couple instances, one in 2022 where they lost like 30 satellites all at once that basically the atmosphere expanded too much. There's too much atmospheric drag, and the satellites just sort of spiraled into the atmosphere over time. And earlier, well, I guess last year, not earlier this year, but later last year, another like dozen or so all entered the atmosphere over the course of a few hours. Again, because of atmospheric drag, decayed their orbits, and they weren't up where they needed to be. And so to mitigate that, well, you need to be in a high orbit. And so for the space station, actually, there's engines on the space station, little motors that basically boost the altitude every few months. Because over time, atmospheric drag, it's going to get lower, lower, lower. So you need to boost that up to not basically burn up in the atmosphere. And you have to monitor that. And often there are more up boosts during solar max and during solar minimum because again the atmosphere expands during solar maximum. Okay, so in the atmosphere we have we can think about what happens. What are the effects of solar max and solar flares and coronal mass ejections in the atmosphere? And so one is GPS errors. This is a big one. So GPS satellites are high above the atmosphere, but they communicate with things on the surface. And so those radio signals pass through the atmosphere. And so in the upper atmosphere, there's a layer that's basically an ionized layer. And so that's the part of the atmosphere that absorbs all the X-rays and most ultraviolet light that's produced by the sun. And so it's a layer of ionized gas high in our atmosphere. But the GPS signals have to pass through that ionosphere. And the presence of that ionosphere basically changes how the radio waves pass through. And so as the ionosphere changes with the solar cycle, it gets more ionized when you have more solar flares and more of these active regions in the sun. You have basically more ionospheric density, and so you got to as your GPS signals pass through there, they're gonna pass through differently than the solar max. And if you have a solar flare, you can have basically what we call scintillation, but regions of the ionosphere that's more ionized than the region next to it. So basically, you'll have these weird irregularities, usually call them, and then that's gonna basically again bend your radio signal to pass through the ionosphere in sort of unexpected ways, as that leads to position errors, basically. And so that if you're using GPS for airplane navigation or ship navigation or even surface navigation, you can have position errors of hundreds of feet, up and over 100 feet, which can be a problem. And I saw an article recently about farmers having an issue during solar max because these big industrial farms just use these remote control tractors that are guided by GPS. And if they lose lock on the signal, they just sit out there in the field and don't know where to go. Let's see, there's also what we call radio blackouts, so high frequency radio blackouts. And so radio waves from the ground can bounce off the ionosphere. So basically, they're bent enough so they come back down. So this enables over the horizon communication, very useful usually. And more ionization in the ionosphere during solar max allows higher frequencies to bounce. You can communicate at frequencies during solar max you can't do at solar min. But too much ionization at too low an altitude is a bad thing. So when you have a solar flare, you can have ionization lower than normal, And if that happens, then the radio waves are absorbed by the atmosphere and they can't propagate at all. And so you can have radio blackouts, which is bad if you're relying on radio communication um, uh, for navigation or whatnot, or just for communication things. Let's see. And so there's also some effects on the ground, so that impact us and our technology from solar flares. And so one of the biggest concerns is the effect on power grids. So during geomagnetic storms, where basically the aurora goes to lower latitude, you have large electrical currents flowing in the ionosphere. And basically, whenever you see an aurora, there's going to be an electrical current flowing in the ionosphere. And so changes in those currents in the ionosphere can induce currents in long conductors near the ground, such as power lines. And so there's been several instances documented, and one of the more famous ones. It's been a while ago, but in 1989, there was the induced current basically overloaded the transformers in the Hydro-Quebec power system. And so basically, I think it was something like 6 million customers lost power in March. So it's cold in Quebec in March. And for about 9 hours, there was no power because the transformers basically blew up. And so the top picture here is basically not a very good picture, but a picture of one of the transformers. You can see that it's not supposed to be all black, and all these wires aren't supposed to be all going different ways. It should look, just like a bunch of nice clean wires, but not so much the case there. And so here's a map from this is a report put out several years ago, but basically highlighting the vulnerable regions in the U.S. power grid. And so they highlighted that the Pacific Northwest and basically the Northeast could be vulnerable to these same sort of effects where you have changing currents in the atmosphere above these regions can induce basically large currents that can overload the power systems there. Okay, this is a while ago, but for hundreds of years, this has been an issue. So for telegraph systems, so we don't have a lot of telegraph systems anymore, but they're sort of analogous to our power systems. But before the satellite era, this was an issue where geomagnetic storms could affect telegraph systems. And so there were two notable events where this happened in 1859 and also 1921, where basically you had these huge induced currents in the telegraph lines, and some of the telegraph stations caught on fire because of things got too hot and overloaded. And it also is estimated that both of these events in 1859 and 1921 were much stronger than any events we've seen since. So much stronger than the 1989 event, that caused 6 million people to lose power. And so we can look even further back in time by measuring isotopes, which we think are caused by energetic particles, hitting the surface. Actually, we look in tree rings and ice cores and sediments. We can look at how the numbers of those isotopes have changed, and that's an indication of strong events, strong flares that could have happened in the past. So we want to know when these things are going to happen, and so there's international efforts that go on for several decades to predict, these solar flares and coronal mass ejections and their effects on Earth and Earth assets. As this falls under the umbrella of what we call space weather. What are the effects of the solar activity, things in the sun? How does that and CMEs, how does that stuff affect the Earth? And so in the U.S. we have NOAA, which usually predicts our weather, but they also have a space weather prediction center. And so this is just a snapshot of their website at NOAA for the Space Weather Prediction Center. And so they monitor the sun and solar flares and solar wind and coronal mass ejections and Earth's magnetic field and the aurora, and try and to monitor all those, and then predict and give forecasts for solar flares and geomagnetic storms, which are used by governments and power companies and utilities and satellite operators and even people just to want to watch it for fun. that are interested in space weather. Okay, so I think this brings me to my summary. Basically, solar maximum, what is it? So it's characterized by an increased number of sunspots, but associated with that are prominences, solar flares, and coronal mass ejections. And these happen every 11 years or so, but the duration of the maximum can be a year or two. So we're in, maximum started in 2024. We're still in the maximum in 2025. Maybe they'll go throughout this year. We'll see increased number of flares and sunspots and all that. It's caused by these cyclic changes in the sun's magnetic field that causes the solar cycle. And the energetic photons, energetic particles produced by the sun's activity can affect us and our technology in space, in our atmosphere, and also on the ground. And so we have evidence that historic events have been much stronger than anything we've seen in the past few decades. So it's really important for us to monitor, understand, and predict the solar activity and the geomagnetic effects. Basically for the safeguard, for the benefit, and to safeguard our technology, and basically our society is so reliant on technology now. If we were to lose power, that would be widespread. That'd be a big hit, and so it's important to try and understand all of this. Okay, so I think that is all I have to say.
All right, Matt, this time I remember to unmute myself, and we do have a bunch of questions for you.
Okay, okay.
Is there a way to be aware of visible aurora displays in Northern California?
Yes. So I guess one thing is so again, there are predictions of where the aurora may occur, and so you can see maps. If you can see the maps like this, where I have a maps of the U.S. and where the auroral oval is, or where the auroral zone is, and this is probably you can try and see if you hear in the news, oh, there's a big solar flare, oh, there's a big geomagnetic storm or something like that. You can go look for these maps at NOAA and other places, and they can give an indication if aurora is predicted to be seen somewhere near here.
All right, and another one was the images you showed, and I think this was towards the beginning. How were they obtained? Ground-based telescope or spacecraft?
So almost all the pictures of the sun were from spacecraft. And so we have spacecraft orbiting, well, some orbiting the Earth, looking at the sun, some orbiting the sun, looking at the sun, that takes the pictures in all these different ultraviolet and X-ray wavelengths. Because it turns out we can't really see in those wavelengths from the surface because the atmosphere blocks a lot of it. Well, X-rays and ultraviolet light. So if we get above the atmosphere with space-based telescopes, we can see all that. And I didn't mention it, but there's one spacecraft. It's called Solar Dynamics Observatory. That's where most of the images that I showed came from, and it's been orbiting. It's been staring at the sun for, gosh, well over 10 years. But taking these beautiful high-res images of the sun, like every couple minutes, of in many different wavelengths, but primarily in ultraviolet and X-rays to see all this structure.
Okay, and I think you touched upon this a little bit, but someone asked, is there any warning system that is used to predict the more damaging effects of solar activity? And if so, how far in advance of the impact can there be reliable forecasts?
So good question. So yes, warning systems do now exist. And let's see. So the Space Weather Prediction Center will make predictions 1 day in advance and 3 days in advance, and much more beyond that. The prediction, well, just like with the weather, the predictions get worse. But yeah, they have their 1 day and 3 day predictions, and usually if it's a coronal mass ejection, we can have it takes about a day for it to go from the sun and reach the Earth. So they have good warnings on that. Solar flares are harder to predict, but whenever we see these big sunspot regions, people are watching those and trying to predict. Okay, there's a chance of flares in the next 24 hours. 50% chance or 30% chance. So they'll put some number on there to sort of
Okay,
try and put a prediction on there.
almost out of time. We got a few more here. Do we have a prehistoric record of large CMEs hitting Earth?
So yes, well, it's spotty, but some people, again, looking at isotopes and things like tree rings and ice cores, they think that they can correlate that with the energetic particles from solar flares and coronal mass ejections is what's causing those isotopes. And so yeah, there's a whole area of study of trying to piece those together from basically yeah not really geological but tree rings and ice cores and some geological evidence. Yeah.
All right, and any findings on solar activity effects on human and animal energy levels and health?
Ah, so nothing definitive. Um, there are people have been looking into that, have tried to look into that. Are there effects on human health and nothing that we can definitively put our finger on because again, uh, in the absence of big long wires on the surface of the Earth, not many of the effects reach the surface. They reach the atmosphere because see them through aurora, but not many effects reach the surface. And so it's been hard to pinpoint any biological effects on humans or animals due to the things like solar flares and CMEs. But I think there still are people looking at these trying to look at these biological effects.
And does climate change affect any of this ionization? By that, I mean, do greenhouse gases make the ionization stronger or weaker?
So good question. So it does not. So the well, that as far as we know, it does not. So a lot of the greenhouse gases and the effects that we see on our climate are within the first 10, 15 miles from the Earth's surface. And then the layer of ionization is up at maybe 50 miles. And so a lot of effects, how the greenhouse gases and climate change is relatively close to the surface compared to the effects from the sun. And that's not to say there might be some long-term effects, as you know, composition of the atmosphere changing would change the upper layers of the atmosphere. But right now it doesn't seem to be the case because there is such a large altitude difference between like where the major effects of greenhouse gas and climate change are occurring, and then the layers where all the ionization is.
All right, and the last couple, how many satellites are outside of planet Earth, and what happens to those outdated satellites? Are they recycled, or are these satellites floating as garbage in outer space?
It's depressing to know how much garbage is in outer space. There are many hundreds of dead satellites orbiting the Earth, and they're just up there orbiting. There are people that keep track of all this. All these just basically big hunks of metal up there orbiting the Earth. Every once in a while, atmospheric drag will make them burn up in the atmosphere, but their orbits are high enough they'll just stay there uh, for billions of years, basically. And there's a lot of stuff up there that's just yeah.
All right, and here's the final one, and it's a good one. Is it true that one day the sun will die?
Ooh, yes. It'll be a long time from now. The predictions are we got about 4 or 5 billion years left before the sun goes out, and so yeah, yeah, it'll happen, but I won't be around to worry about it. Hopefully, we'll be somewhere else by then.
Excellent. Well, thank you so much for this really fascinating presentation. Apologies again for being muted at the beginning. I'm going to send you everybody a link to the recording as well as the slide deck. That'll come to you tomorrow. And we appreciate you being out here, and we'll see you next time. Thanks very much, Matt.
Sure, thank you.